Assalamu alaikum wa rahmatullahi wa barakatuh. Allahumma salli ala Muhammad wa ala alihi wa sahbihi ajma'in. Today I'm going to explain what is the abstraction and what is the meaning of abstraction and how it is relevant to digital logic design and how it is relevant even to all of the different fields that abstraction is used. So first I would like to explain what is the purpose of learning about abstraction. Abstraction gives us a better overview understanding of why we are studying digital logic design, or why we are studying different subjects in our course, for example, electrical engineering or any different course. So that is the reason that I want to explain what is abstraction means. What does abstraction mean? So first let's begin with a definition of abstraction. So here, one of the definition of abstraction is the abstraction process, deciding what details we want to highlight and what details we want to ignore. So it is a kind of layer that we put on one system that we would like to ignore some of the details and focus what is actually important. So with some examples that you will understand much better what we mean by this definition. And the meaning of abstraction in Arabic is tajreed, which means that you throw out all things that are not important for the temporary period, and then you focus on the things that are important. And then I will explain why is this matter and why do we want to do that. Why do we want to ignore some of the details and focus on one thing? So first, I'm going to give an example on digital logic design. So here we begin with lowest level of abstraction, meaning the most basic level that we can get to. So the lowest level we can get to is the material level. So what do we mean by material level? Material level where we study the semiconductors, we will study the transistor. So here we actually study what is actually the resistance. So here most of the physics is involved, studying the materials properties and why do they behave the way they behave. So this level is usually studied in physics too, or maybe in some colleges, the semiconductor physics. So this level focuses on the why more than how can it be used. So focuses on why the resistor behaves in a way that behaves, why it follows Ohm's law, why does it not follow another laws, how an inductor works, how a capacitor works, and so on. So all of these are the questions that are related to material abstraction level. So this level is the closest. Here the closest to the actual circuit that we want to build. Here we care about the different technologies that could be used and how they are used and how they are implemented. So all of the basic questions are answered in the material level. And this is a very complicated level. It's not an easy level. It is so close to the circuit that you have to study so much physics and so much of the physics level that to actually understand how the materials actually behave. So you have to study how a resistor actually impedes the flow of current, how an inductor works, how a capacitor works, and all of the formulas that come with it. Then we go up in the abstraction ladder. So here, what do we mean we go up? So I'm going to repeat this phrase. When I say that we go up in the abstraction level, like this, we go up in the abstraction level, that means that we hide some of the details that are not important. So as the definition says, that we decide we need to highlight some of the details and ignore some of them. So in the material level, we focus on a lot of things that are very essential to understand the material level. But when we go up in the level ladder, in the abstraction ladder, we go to the circuit elements. Here we ignore some of the things that we want. For example, so here when we want to represent a resistor, we do not look at the formulas that actually why the current is impeded and how it is impeded. What are the formulas that governs the behavior of resistor itself, the different materials. We only look at the abstraction, and it's usually represented like this. So this is the circuit elements, is a resistor, and that's it. And then you look at a capacitor. A capacitor is represented like this. And then you have, for example, an inductor is represented like this. So all of these are just circuit elements that are just of some formulas that represent the behavior. So the behavior of voltage and current that represent the behavior of these elements. So you see how we go up from the level of abstraction from material to the circuit elements. Now we go one level up, we're actually dealing with the more complicated topics. So that explains my points, is that as you go up in the abstraction level, as you go up here, the complexity goes up as well. So the complexity complexity goes up, goes up. So it means as you go up, you are dealing with more and more complicated topics. So that's why exactly you need to hide out some of the details, because it's simply you cannot focus on all the details at once. So if we would like in the circuit elements, every time that we would like to use a resistor, to think about the material that is used and think about all the formulas that govern the behavior of them at the material level, then it would be too much work and too complicated for the purpose of the work. So then, the second level we said is circuit elements. Then we go one level up, which is the gates. Here we abstract it even further. It means that we hide some more of the details. We look only at just gates. So it could be an AND gate, it could be an AND gate, it could be an OR gate, it could be an AND gate, and so on. So here, some of the courses, even our course, started from this level. So it did not start from this level, the circuit elements. It did not start from circuit elements. It did not start from circuit elements or material level. No, it started from the gate level. So gate level is simply just an abstraction of what is level behind it. So when I think of an AND gate, I do not think about how is it actually implemented, what is the technology used, is it CMOS, is it TTL, or what is the material used, and so on. All of these levels are just hide out. So as you go up, so now we are on the gate level side. So in this level, we do not think about all of the previous things. We think about just the gate itself, the behavior of NAND gate. We know, for example, an AND gate, we know the truth table of it. So here it's only true when 1 and 1 is 1, which is the logic signals are true, then you will have true. So you're not thinking about how is it actually implemented. Do we use resistor implementing it? Do we use a transistor? How is it actually transistor? So all of this is just hide out. Now we go up again. We go up in the abstraction level. We go up one more to the register transfer level, which is RTL, is abbreviated as RTL. So here in register transfer level, here we are abstraction even more. Here we are thinking about where the information is stored and how can we manipulate this information. So it says, so a register is just a piece of let's say a connected dates together that form something that is actually can store data using sequential logic. So a register is used to store some of the data, and then we can what we can do is use that register to transfer level from one place to another to do the things that we want to do. So here again we go up again in the abstraction, in the complexity and the abstraction level. So here we are now, this is register transfer level. Then again we go up to algorithms. Here we are dealing with not even with the register transfer. Here register transfer even is actually complicated to deal with. Here it's similar to the machine language. You have to know each register and how to transfer information, how to deal with a machine code. But here in algorithm you deal with a higher abstraction level. Here you could have the ability to deal with more complex circuits. So then you go again up to system, which is the final level of abstraction in this example, where you go with the deal with the whole system as a whole and how to implement it, rather than dealing with each level individually. Then maybe you can say that the final level in all, which is user level. Here where the actual user uses. So I will give you an example that that explains this topic. So if you are using a computer, do you think about the system that is used? Maybe you do, but do you think about the algorithms that is used? Do you think about register transfer level? Do you think about the gates, circuit elements, material, all of that? You never think about it because we simply, as an engineers or as a digital logic designers, used all of these abstractions to just hide all of the details that is irrelevant to the user. So it's simply just a computer here. It's simply just a computer that is used to display things. That is just an abstraction of what is actually done. So you have a mouse, a keyboard, and inputs, and then you have the outputs and that thing, and that's it. You don't have to think about the register transfer level. You don't have to think about gates, circuit elements, material, none of this. Only thing that you have to know is how to use the computer. use the system, how to interact with the operating system. And that's it. That is just the gist of the idea of abstraction. And the reason behind doing this abstraction is it is just the only way of doing it. To deal with the high complex circuits, like building a computer is a very complex task. Doing it in this level of abstraction is the only way to do it. Because if you want to build such computer, and the first thing you think about, or if you don't have all of these levels, the material of the logic gates that you're going to use, then you will never be able to build such computer, because it's too complicated to think about. It's just the same thing as saying, if I want to, for example, if I want to build a city, and the first thing I want to think about is how many peoples, or not how many peoples, or how many doors there will be in each room, in each of the buildings. Well, that's not very important now. We only think about the levels of abstraction that's very high. So, for example, the city planning and how the different buildings will go in the city. And this is the same. So, in real world, when we want to design any product or any computer or any microchip or microprocessor, we begin with a very high level of abstraction. Then we go down slowly till we get to the material side. Then you have logic gate designer. They have to think about what is the material used, and what is the circuit elements that you have to be used, what is the gates, and so on. But what we start with is the higher level of abstraction. Then we go down slowly till we get to the final product. So I will show you a picture that illustrates some of these principles. So first, let me make this more clear. So here we have different domains of abstractions. We have here one domain. One is behavioral domain, which is the behavior that you want to do. Here were some of the things that I explained. And then you have structural domain, and then you have the physical domain, and all of them explaining how actually products are implemented, how they're actually done. So first, let me begin with the behavior domain. So first I begin with a specification. What do I want this device to do? What is the reason I'm building this device? Then I go down a little bit to the algorithm level. Then I go to register transform, then Boolean algebra, then differential equations, KVL and KCL, and then go finally to circuit levels, which is the basic level, and then you have to the material level. And the same is structural. You begin with CPU memory, you begin with the higher level abstraction, then the processor, then the state machine, then gates, then transistor, and so on. And this is how it is. So you begin from the higher level and then go slowly as you go down and down to the final abstraction level, which is, let's say that it is the material level. And that's it. And this idea of abstraction is not just relevant to digital logic design, it's relevant to everyday life. All of us use abstraction in some way or another. So when you use your car and turn it on, you do not think about what is happening, how the motor is running, and what is actually happening inside the motor. You only think about it as an abstraction, as just a car that takes you from point A to B, and that's it. All of the things that are displayed to you is just an abstraction of what is actually behind it. And if it was the other way around, that every time you have to use a car, that you have to think about every single piece that goes into the car, then it would have been impossible to design such product. And that's it. If you would like to dive deeper into abstraction, I would link some resources that are very useful and some videos that I used in explaining this video. And even this image came from that video. And thank you for listening.